Ladies and gentlemen, please allow me to first read the agenda for today hybrid meeting. The first agenda is the opening session. Second, we will have a presentation and discussion session led by our moderator. And the last, the closing session. Ladies and gentlemen, please allow me to read the webinar rules of conduct to the participants who attending in Zoom application. Please mute your PC. If you have any question, please type your brief question in the chat box and use the raise hand feature on the Zoom meeting. Please use the virtual background and all participants are welcome to change the name into name_ your institution. Alternatively, participants can join the webinar through YouTube BRIN Indonesia if there's not enough Zoom capacity. Before we proceed with our first agenda, I would like to invite all participants to sing the Indonesian national anthem. Please, all right. Ladies and gentlemen, now we are in the opening ceremony. As our first agenda is great honor to invite the acting head of the Research Center for Geological Resources BRIN, Bapak Dr. Insinyur Nur Cahyo Arianto, to deliver some welcome remarks open today's webinar officially. I want to inform to everyone that Bapak Nur Cahyo is not attending yet in this room. I would like to the next session. Ladies and gentlemen, before we begin our main agenda, now we will be taking pictures together to the participant who attending in the Zoom meeting. So please remind them to activate the camera, the function on your Zoom application. I would like to invite the IT team to assist in picture. Please be prepared and wait the moment and hold your best smile. Please, Kang Haris.
Okay, thank you. Please wait a minute. Screenshot it. Okay, ladies and gentlemen, I will to take picture. Please open your camera to smile. I have two slides. Slide 1, 3, 2, 1. Slide 2, 3, 2, 1. Thank you, ladies and gentlemen.
Okay, I will be done taking pictures. Thank you for your cooperation. Ladies and gentlemen, in this guest lecture, we will have a presenter, Professor Kaswaki Kweke, Chair of Earth Resources Sciences, Head of Division of Civil, Environmental and Resources Engineering, Graduate School of Engineering, Kyoto University. The presentation and discussion will be The presentation and discussion will be presided over by Ibu Dr.
as the moderator, but before that, please allow me to read the Dr. Santika Mayani dari Sudarto, she is the director at the Research Center for Biological Resources BRIN. Her educational background is as follows: received a PhD from the Department of Urban Management at the Graduate School of Engineering at Kyoto University. Completed the geothermal master program at the Faculty of Mining and Petroleum Engineering at the Badan Institute of Technology. Graduated in Meteorology Science from the Faculty of Earth Science Technology at the Badan Institute of Technology. And also research activities in 2024. First, there's a fellowship, Delta and Kyoto University 2024. Second, geothermal dialysis, geochemistry for balance therapy of the hot springs. The third, geothermal dialysis, revealing fascinating biological phenomena of hot spring and rock carriers. And the fourth, the development of retort technology. This is solution that prevent respiratory disorders caused by mercury vapor inhalation by small-scale gold mines, BRIN and Gorontalo State University. Okay, Bu Santika, I will present for you. The stage is yours.
Thank you, Ibu MC, Mbak Nurfia. But firstly, I think Pak Haris, the online participants say that the sound is not really clear on the Zoom meeting. So should we try it just online?
No.
Okay, while we are waiting. Okay, first and foremost, we are so honored to have Professor Koike Sensei. I mean, Professor Koike, because usually we call you Koike Sensei. Professor Katsuki Koike from Yuki University is accompanied by Dr. Kashiwaya atau Kashiwaya Sensei. Dr. Koki Kashiwaya is Associate Professor at the Graduate School of Engineering, Kyoto University. I'm also thankful that one of our alumni from ITV, from engineering ITV, is also here with us. Thank you, Bapak Heru Berian Pratama, one of the lecturers from Geothermal Master Program ITV. Invited esteemed guests, good morning. I would like to check whether the sound in the Zoom meeting is already clear?
It's clear. Yes, yes, you can hear it. You can hear your voice.
Okay. Thank you.
Yes.
So I have seen
Betul.
Bapak Nur Cahyo as the acting director of our research center. I think Pak Cahyo.
Yeah, thank you, Dr. Rios. Is my voice is clear, son?
Yes.
Yes, Pak.
Okay, thank you once again. First of all, I would like welcoming or opening remark to Honorable Professor Koike and his staff, and also from the ITB, my colleagues of ITB. The warmest welcome at our office in Bandung. Thank you for your coming, and really my deepest apologize for because I couldn't have the opportunity to meet in person, yeah, due to other assignments. So I have to in Jogja to attend in with the maritime and investment ministry. By the way, thank you once again for your sharing your knowledge and this morning's and webinar with the title was the advanced spatial model of mineral and yeah, hello.
Yeah, please continue.
Yes, thank you. Advanced spatial model of mineral and geothermal resources by applying machine learning based method. Okay, and I hope this discussion this morning could be led by Dr. Rios, and I think she's also capable of it, this topic. So once again, I will give you your permission for a moment to attend another Zoom discussion. So Madam Rios, could you proceed? And thanks again for the opportunity. Thanks, Professor Koike and the other. Thank you.
Thank you, Pak Cahyo. Okay. I think geothermal is my thing, but machine learning is a really new thing. So I think I would like to have more knowledge of this. So I would like to, of course, learn a lot from Professor Koike. Machine learning is a game changer, of course, in various fields, revolutioning how we analyze data, make predictions, and automate process. And discovering and developing mineral energy resources like geothermal is crucial to meeting the world's increasing demand for raw materials and green energy such as geothermal. So using methods based on machine learning for spatial modeling is one of the most exciting new technologies in this era. So welcome to this exciting guest lecture on machine learning application in geoscience. I am Tentang. You can call me Rios. Today's agenda will include a 45-minute presentation and Q&A session. Please hold your questions until the end of the talk. You can type it into the chat box if you join us on Zoom or YouTube. On the Zoom meeting. Is my voice clear over there on the Zoom meeting?
Yes, clear.
Thank you. So before this lecture, I'd like to highlight some of Koike Sensei extensive accomplishments, Professor Koike. However, I only be able to touch only a few key points from his resume. Maybe Mr. Haris could show the CV. Professor Koike began his academic journey at Kyoto University, earning his bachelor's degree in mineral science and technology, his master's degree in engineering geology, and doctorate in engineering in 1995. International collaborations, such as visiting researcher appointment at Stanford University and numerous scientific research projects, have enriched his career. He held leadership roles in academic and societies, including President of the Japan Society of Geoinformatics 2021 to 2024, Vice President of the Mining and Material Processing Institute of Japan 2023 to 2024, Honorary Professor from Bandung Institute of Technology in 2024, and recent recognition in this year includes the commendation in research category of education, culture, sports, science, and technology, or MEX. His substantial contribution to academic discourse includes serving on editorial boards of prestigious publications, which earned him the Natural Resources Research Exceptional Reviewer Award and the Japan Society for the Promotion of Science Evaluation Committee Member Award in 2017. Last but not least, he was awarded Ganesha Wirya Jasa Utama in ITB in the same year. So having Professor Koike with us today is a great privilege. Let's give him a warm welcome. Okay. Yes.
Okay, thank you very much for the kind introduction. It's my great honor to be here, and I appreciate greatly the invitation to the demonstration using simple things. So today, my talk is machine learning technologies affecting food and neuroimaging. So first is proposing to a piece of artificial intelligence. But artificial intelligence is a too wide experience for me. Well, that's why I just focus on the machine learning that is one the field of work, artificial intelligence. So first, I want to introduce So this video about internationally student sections of university. That is because there are about 2010 students about that is something that we it's about the house. The international no voice. Okay. Okay.
I think I may take out the
Bisa. Iya, bisa pakai move soalnya nih, move. Move. Ini kan aku ini aja spesimen deck stripping 900 liter ini manual bisa.
Ya, boleh. Saya matiin aja sih.
Biasanya kan kalau geohistory itu kan cuma titik sumur kan yang di backstrip ini. Kalau di sesi masalahnya ini kompaksinya.
Ya, kompaksinya.
Nggak terini tuh karena makanya untuk ada penelitian itu kurang dari 20% uncertainty ya. Mungkin pergerakan ya kompaksnya yang diakibatkan displacement ring. Kita terlalu panjang ini kalau bahas kinematik sama evolusi center ini.
Terlalu banyak.
Banyak kali loh. Ini sendiri loh kan. Untuk bicara kinematik aja sendiri judul kali orang ini tambah lagi.
Can you hear my voice? Okay, thank you. For the audience. So hopefully that you can hear. 聞こえないですか？聞こえた？いや、no. Just media player. Sorry, this is just
yang jelas-jelas dapat dana dari rumah program di Alus Miswanto, yang dia sebagai kepala tim nanggung anak-anak buah.
Okay, I'm sorry for this disruption. Please wait a moment.
ready. No, terima kasih. I'm sorry, take a time. So now it's okay. Please wait a moment, just a few moments. Watch it. Oh. Sudah baik itu. Okay. Okay. Thank you. Sorry, this is a trouble to show the video. At first, I would like to introduce my lectures, and after that, I'll show you introduction video of my lab.
Masa sekarang saya sama.
Saya takutnya pakai laptop untuk bisa
Tapi harus pakai ini maksudnya clip on, jadi nggak gitu kan, biar jelas. Oke. Jangan. Maksudnya? Kan sih nggak ada suaranya gitu ya. Oke, ini gimana?
Hubungin ke connecting to USB.
Tapi tadi kalian masih nggak kedengaran?
So just now, this share screen and this share screen is different. This now. Yeah, no. Okay.
We are here. Can you hear my voice?
Yes, it's better.
Okay, I'm sorry. Waiting for 20 minutes. Today, my talk, advanced spatial modeling of mineral and geothermal resources by applying machine learning-based method. So the background to this research, we want to know the regional imaging of the Earth's interior or subsurface structures with high security or geological structures, physical and chemical properties, or grade and the compositions of petroleum and geothermal reservoirs. Now, these features are required in the Earth sciences and the engineering field. So, but our data are usually limited in number and locations. and distributed bias and sparsely. The challenge is how we can get the plausible and precise geological structures, sciences, properties, using this limited number of data and locations. So that's why spatial modeling, advanced spatial modeling techniques for constructing, reconstructing correctly the true distributions for irregularly spaced point data has been more and more important. So the final goal of our research is clarifications of resource generation mechanism and the deposit formation process by highly accurate spatial modeling techniques from these limited and sparse geological related data. So for this, we try to develop geostatistical and machine learning based method in considerations of geological distributions, scaling along spatial correlation and multiple geophysical and geochemical data. So as I said at first, today the Ryo-san invited me to present artificial intelligence, but this topic is the very wide discipline. That's why I focus on just machine learning techniques. So today's topics composed of four. The one is deep, the neural network with variable structures and influence factors and sensitive vectors. These techniques apply to the critical deposit. One is VMS, deposit areas, and the impurity content in limestone. The next one, this is the original method, the neural kriging. So this is a combination of geostatistics and neural networks to get more accurate estimation result. So these techniques to consider the same variogram into deep neural networks. So these techniques is applied to the seafloor hydrothermal deposit and the surface temperature. The applications of geothermal resource exploration. And the third one is, but I'm not sure this technique can be included in machine learning, but in the official meaning, this clustering is categorized, classified into the machine learning method. The clustering and the spatial modeling of clusters using geostatistical simulations. This techniques has been applied to the rare earth element. Rare earth element is very crucial for the advanced industries and technology. And Japan tried to find out the rare earth element in seafloor mud sediment. Finally is applications of remote sensing, spectral and spatial downscaling of multispectral remote sensing images. These techniques has been applied to the hydrothermal and the SEDEX deposit areas. So these techniques are the applications I and my laboratory want to contribute to the sustainable society with the mineral and geothermal resources. So artificial intelligence, composed, basically the rule-based method and the machine learning method. And there are several categories of machine learning. One is regressions, classifications using clusterings of other traditional clustering, and the classification, clustering, and recommendations, and the dimensionality, the reductions. The PCA is one of the traditional dimensionality reduction method. And the another approach is deep learning. As you know, the most typical, the representative method is neural network. So at first, I would like to introduce very briefly about the method we use. The one is geostatistics. Many of you know already geostatistics. The geostatistics based on the technologies, spatial correlation structures of the data. in this method, the most basic the quantities is same variogram. But same variogram is statistical quantities for the spatial correlations in sample data. The definition is like this. It is very simple. The calculations expectations scale difference of data pairs separated by distance h. And the spatial estimators based on same variogram we use generally the Kriging method. The Kriging method is assigning optimal weight to each data sample. So that is the random means weight, and this weight can be calculated through the same variogram or the covariance. So next one is the artificial. The one of the artificial intelligence method that is the neural network. So the fact is the merit to use the neural network over geostatistics. So the geostatistics is based on the spatial correlation structures, but the statistics cannot be used directly. The data value, all data values that need to be transformed at first the spatial correlation. On the other hand, the deep neural network is in short DNA that can incorporate the spatial criteria specific to the particular problems in addition to the general criterion of errors. So I will introduce more details about this aspect. And the DNA can consider the physical laws that control the data in a particular estimation in the field of geoscience, geothermal science. That this laws is such that conductive and convection beam. And category data, that means that non-value data that can be used for spatial estimations. And the diverse data can be used directly with transformation into statistical quantity, such as variogram. And data that whose spatial correlations is unclear and changeable with locations can be used to this DNA. Examples I have introduced shortly after. And sensitivity analysis and inference factors that can be derived from that analysis of network, such a network. The first applications is that deep neural network is variable structures. So the usual case we use the fix the neural network techniques. At first we learn network structures and learn the weight connecting each neurons. We applied this learned networks for all the data. At first we learned that we fixed that is DMN that is used to the all areas and all data. But in the field of geology, but this network, of course, can be variable with locations. Some locations, the fault structures is influence factors to determine spatial correlations, and other areas such as geological structures is more effective, more has the higher the control the effective influentials for the spatial estimations. Now that's why we repeatedly change the network structures. But it means that number of neurons in the input layers and the number of hidden layers to run the network structures. So for this case, the input factors is the cross validations. So usual case, the network run is based on the minimize that output errors that are this one. So for these cases, the O is that output from the run, the network, and the V is the actual data, the data we use for that. But and as I said, that this the output, the values, the changeable with of course the network structures. So the variable structures means that we change the search areas is like that, and that we determine that the optimal search areas which produce the minimum output errors, and determine the structures which produce the minimum output errors. Now, for this case, this is that the MK is that the nearest sample point that is used, or the number of neurons used in the hidden layer, like that. So it means that at each locations, the data for training and the number of data for neurons in hidden layers are changeable. Now, these techniques at first is applied to the VMS that we say the Kuroko deposit in northern part of Japan. The Kuroko deposit is appearances like that, the black, the ores, and it has content of copper, copper, lead, and zinc, the basic metals, and also the precious metals, in particular the silver. So in the northern part of Japan, there were more than 40 mines of this type of deposit. So at first, we thought that with my students that these areas can be used for geostatistics can be used for these areas. But by showing the same value, we were surprised because there were no special correlations. That the figure shows the same value from copper, the lead, and zinc. If there is correlations in these technical component metal concentrations, the same diagram shows just a moment, internet connection error.
Actually, yes, already organized. We even have to see this.
Okay, okay. That was fine. Okay, thank you. So if there if there is correlations, the same pattern shows the increased patterns is like that. But this the figures shows that we said that the pure negative, no correlations. That's why that we gave up to use the geostatistics method. So using such the variable structures of DMN, at first that we consider what kind of data we use to get the reliably or plausibly such metal constellations distributions. And we found that the result depending on the information we use. At first, this figure shows that data only the result. So there was actually the mines, the biggest mines in this PMS deposit. So we can detect slightly of the actual the deposit areas, but the concentrations is not so the variable, not interesting. So the next one is that we consider the data locations and the geologies that you can see that high-grade zones that appear more clearly than that the DNA that consider the data location only. So next one is that we consider data locations and geologies and the ordination index. The next one is that the more information we use, data locations, geology, ordination index, and the gravity anomaly. So that you can see the root mean squared errors that decrease with the number of data information we use. So by considering that many informations that we could find out the actual locations of this maximum, S3, and the other deposits very clearly. But that's why to use such a DNA method, that the data information we use are very important and significant to get a good result. The next one is that the cross sections of the estimated the kappa rate between distributions, and but this is that one clearly these continuous distributions of these metal elements. So this is because there is that the fault structures is that. So and you can see this one is that the high-grade ones of zinc it's distributed along the fault is like that. So for this, that we could understand, interpret that this fault that has had the role of the ascent fluids of that the containing or solutions. So the next one is that the horizontal cross sections of metal content at the depths of 250 and 290s. And that you can see that the local high-grade zones here. So it is important that we didn't use actually this mine data. So this is the techniques of extrapolations. So challenge is how we can predict the actual locations of metal deposit using data outside the deposit. So these techniques they can successfully extrapolate of the data to locate the actual locations of metal mines. And by the analysis that the network that we could determine that find that influence factors on the content estimations. The fact the geological or fault or geochemical or geophysical the factors, the sum. What is the degree of these the multiple the informations on the metal content distributions. So this very colorful figure shows that each the influence factors. So this number 1 to 25 means that rock type. You can see that the high grade zones is like that, and colored by the colors green and this pink. So this color means the distributions of dorylite and distributions of dayset. From these figures, we could understand, we could interpret that such dayset and dorylite had the strong influence of the metal deposit, metal constellations. So the next one is that the sensitive vectors The sensitive vectors means that that this one and this one is that. So the where the high grade zones, that it means that anomaly zones is located. So in these figures that this is one main areas. So you can see the most sensitive vectors directed upward, and this one is a downward. So this upward means that the high grade zones are located in the upper part of deposit here. And this downward, the vectors mean that these high grade zones, anomaly zones, are located in this one is the lower part of the deposit. So from these vectors, our interpretation is like that. So this one is that some proper genic massive sulfide deposit. And this the VMS deposit generated with mixtures of seawater and or solutions. Now this vector suggests that these mixtures occur at the top of sea bottom here. And this figure shows that these mixtures occur something like the deeper zones, below the sea floors. But that's why this the city vectors can be used to interpret of generation process of this deposit. So such a same procedures, the variable structures of DNA was applied to the impurity content limestones. Because as you know, limestones is composite calcite. And the content of the sea, the carbon, I'm sorry, the content of calcium is the key factors to determine the commercial values of limestones, and also the impurities such as the phosphorus and silica and iron and the manganese. They're also key factors to determine of limestone the values. The limestones with small content, few content impurities, the commercial value is high, but the limestones with high content impurities, commercial value is low. So to identify the impurity distributions, we consider such lithotype, the geology, the rock type, and the fossil type. The fossil type, this is because fossil type determine over that the age, geologic age of limestones. The 10 limestones was formed. For example, the lower Permian and the middle Permian and middle Carboniferous and upper Carboniferous. So the changing geological the age also related to the changing of the source of limestone. So this is that the metal structures or variable DNA. As you can see, the number of neurons in the middle layers that change 1 to 10, and the number of sample data for training 3 to 12. And as you can see, the same as the previous the case, that with increase in our informations, our estimation errors decrease. It means that our estimation accuracy, the increase is information for use. Here also the same value is not good. This is because that spatial correlations magnetic effect is very large. It means that the impurity content that has very weak, the spatial correlations is not good for geostatistical applications. So here that we compare the result by this one is the kriging method, traditional geostatistical method. And this one is the variable, the DNA method. As you can see, the general trends are same. And the high impurity zones and the low impurity zones are almost the same. But as you can see that the DNA method shows more complicated structures. more changeable structures of impurities. And also, there are no data here. As you can see here, there's no data. So for this case, no sparse data areas, the geostatistics is very weak because the nearest data are extended to far away for the areas with sparse data areas. But the DNA can consider the lithotype, geology, and fossil type. That means that the geological age. Well, that's why the different results can be obtained between geostatistical method and the DNA method. This comparison is extended to horizontal cross sections, as the same as the Kriging method and the DNA method. Now you can see the, for example, for that the Kriging method, the color is just one here. But for the DNA method, color is different, mixed color. It means that different in impurity content. Now, this is just how to say spatial calculations is not so interesting for scientific features. But if we consider that influence factors or impurity of limestones, that shows some scientific interest and scientific values to this how to say resource geology. So for this case, this figure shows that the fact is that the initial factors, influence factor, the class A, the colored by the blue is that just a coordinate. It means a data location. So it means that the correlations of data is most important for that impurity content. The second one is that B is the rock type, except for the crystalline limestones. The class C is a fossil type. It means geological age. The geological age that had a strong effect on impurities of limestone. The class D is the crystalline limestone. The crystalline limestone is similar to the marble, the very beautiful limestones. So for the case of, for example, phosphorus, phosphorus is the most important the impurity to determine commercial value of limestones. So for this case, the class D here, the common to the all impurities, that is crystalline limestones. It means that alteration limestones by the heating. So this heating determines the impurity content. So, and in the other hand, this is the B, C here, C colored by red here, is that fossil type is means geological age. So, that's why we could find out that this part is the alterations, regional alterations determine impurity, that this area impurity determined by the fossil type geological age. Now, this is one of the scientific contributions. So next one is that applications in neural retrieving to metal and geothermal resources. So as I said, the traditional random criteria of DNA is like that, but we can try to minimize the estimation errors. It means that square the errors between actual data, the T, and the output from the networks. We try to minimize all these errors. In addition to these criterions, we add one criterion, the error of the same value here. So it means that our estimated result must satisfy with same value included in the data. At first, we try to, our idea is truly correct or not, or that doesn't have meaning. So at first, we made some spatial model is like that. But this model is perfectly follow the same variogram. We say this is the same spherical model. So this is the comparisons of this neural retrieving And the ordinary DNA means that the deep neural network, and this is the ordinary querying. So as you can see, our neural querying can be reproduced perfectly of the spatial model like that. And this is a reference model. And we try to do many case studies about the changing the data locations. The here examples pattern 1, the pattern 2, pattern 3, and pattern 4. So this is the neural querying and ordinary DNA, and this is the traditional querying method. So as you can see, the ordinary querying and ordinary DNA are changeable with the data locations. For example, this estimated result by the ordinary querying, and this result is quite different because of the data distributions. But the one important thing is the neural querying is very stable. So don't worry about that. Don't depend on data locations. Even though data locations are different, but the ordinary querying can correctly reproduce the reference model is like that. But that's why we believe we have the confidence our method proposed idea is very good. So, and the one point merit to use ordinary querying, it's consider that the directional data is like that here. So this is that just scalar data don't consider that the vector data. But if, for example, this is a data strike and D, and the elevations of data point we measure. So we have the two kinds of data, one direction data and such as scalar data, locations or values. The neural querying can incorporate the both informations by the criterions of the minimizing errors of directions and same variable. So you can see by that directional data that output result is quite different, and that this spatial model can perfectly satisfy that the data directional data assigned to this sample model, difference model. That first case studies the seafloor hydrothermal deposit in Japan. So why this is a challenge? Because that different from the mine areas in land. So number of the drilling data, powerful data are very limited because of the difficulty in surveying in seafloor hydrothermal deposit. For this case, this is a collaborated research with Japanese institution, JAMSTEC. So the area is wide, but there is only 1, 2, 3, 4, 5, 6 data. And this data and this data very distant. Using this just the 6 drilling data, we made variant of copper and zinc. So this is the horizontal directions, and this is the vertical directions. And this is the result of the neural querying. So this is the variable model is orange here, and explain the variable of the metal estimations developed by neural querying is the blue. So this orange and blue, almost match up with each other. For the vertical directions are perfectly matches. That's why just one curve that we could see. So this is also the comparisons of the DNN, the traditional neural network coordinate only. This is the DNA coordinate, and we consider resistivities because metal content is some part due to the resistivities. And this one is a neural querying, and this one is the geostatistical simulation method. So please consider here neural querying, and this one is the traditional geostatistical simulations. General trend are the same, but the different. You can see this sparse data area. So here, So you can see this is this quantity because no data. This locations and this locations, number 5, number 6, is distant here and here. Now that's why geothermal method is weak for the areas with sparse areas. But the neural query we can predict metal content. Now I think that correctly. And we can see that path of the hydrothermal fluid, like that 2 trend, 1 and 2 here. And that is one of the estimations. Because the data is just one directions. So how we can extend this one-dimensional data to 3-dimensional? For the case of geostatistics here, this is neural querying. This is the try to maybe nonsense. Because just one data, one D data. But how we can extend this 1D to 3D? Now, geostatistics is reasonable because that same data extend these directions because 1D data. But we consider additional informations such as topography or geophysical data for neural querying. So using such additional supplementary informations, neural querying they show that high-grade zones is like that. And please see this one is this quantity is like that because of no data. But the neural querying method can compensate such a no data or sparse data area. Now that's why this is one merit to use neural querying. So another merit of applying neural querying method are now my laboratory is making papers of these topics. And soon after, maybe within this June, we complete this paper. And we try to apply these techniques to all Japan areas to estimate 3D temperature informations. This is because that the all data is limited to the depth of -2 kilometer depth. Of course, this data, the well-logging data for temperatures is for hot springs and some part for that, but such as scientific drawings. This figure shows the distributions of borehole data covering all of Japan. So we collected 3 data sources, 3 databases. This is the structures of neural querying at first temperatures at the elevations. XYZ is that the well-logging data location XYZ. And this one is that the supplemental official data to increase the estimation result of the temperatures. One is the subgeology, geothermal gradient, and distance from the nearest active volcanoes and curie point depth, and water chemistry of hot springs such as the pH, sodium, potassium, magnesium, chloride, sulfate, bicarbonate concentrations is like that. So this figure shows that the interpolations and the extrapolations of that neural query. So at first, this one is a base model here. It's the estimations by using well-logging data only. So this one is a curie point depth model, and this is a hot spring model. It means that our information increase. And finally, this is that the old model, this one, colored by red. As you can see, the old model produce the lowest estimation, the estimation errors. So it means that similar to VMS deposit, if we increase that information for that neural training, our estimation, of course, this is the case. Our supplementary data has a correlations with the main target data. In this case, temperatures, and previous case, metal deposit, metal content. So the all information have correlations with the temperature, subsurface temperatures. That's why with the increase in the information, that decrease estimation accuracy, the estimation error. The final result is like that. So this is the temperatures minus 1,000 meter, minus 3 kilometer, minus 5 kilometers. Now it is interesting that minus 5 kilometer, there were only 4 data. Minus 3 kilometer, just 15 data of the temperature. But using auxiliary information, we could get very plausibly or confidential or reliable data temperature distributions is like that. Just a 4 data, but this is our estimation. Something like that, surprising. This is the high hot places, hot zones, and this is just DNA using the temperature, real temperature data only. So no auxiliary information such as geology, Curie point depth, water chemistry, we didn't use. So please compare this one and this one. The temperature distributions is quite different. This is because this estimation based on many information. That's why we could understand that the neural-based estimations needs very good information, supplementary information. So finally, this estimations is applied to find out critical point of waters. Now this is because Japan in similar to Indonesia, promote geothermal power generations. But due to some social circumstances, it is very difficult to produce new geothermal power plant in the greenfield zones. But that's why I think that the supercritical power generations at the present, the geothermal power generation plant is more preferable. That's why I try to find out where the locations of supercritical from the conditions. So the figures show that isothermal to reach this water the supercritical conditions here. So from this figure, we could understand, or we can estimate where is the good place for the supercritical geothermal power plant is like that. This is just one applications. So the 4 applications, just for a minute, the detections of the mineralized zones through clusterings and special model of the clusters. So as you can see, now Japan needs rare earth element in the matrices. And as you know, our target is composed of yttrium and this traditional random. So our target is that we cannot say clearly where is our target, but still some secret matters of Japanese government. So, actually, our target is EEZ, exclusive economic zones of Japan. So, this is deep sea for topography and the PCA principal component analysis of their element. So, usually this one is the result of PCA. So, because that the old rare earth element that has strong correlations, very strong correlations, the linear correlations over 0.99 like that. But that's why the most information is concentrated in PC1 here and PC2. So this is a very simple classifications, the PC1 and the PC2. So we can see that this one is PC1, is that this is the PC2, and this one is the PC3. So this one is for the case of the PC1. Is that sorry. That in this case, the cluster 2 is that good correlations with the locations of high and extremity the rare earth zones, rare earth element zones. So that we focus on the where is the PC2, the zones are here. So that this one is PC2 is the high grade zones of the rare earth element. So now this is the locations of that the simulations of geostatistical simulations in here, all rare earth element constellations and the distributions of clusters here. So we can see the where is the cluster 2 here. And this one is that this one is the distributions of rare earth element. And this one is just the PC1 score. And this one is the distributions of cluster 1, 2, 3. So we can see that this, as I said, the cluster 2 is the most hopeful area. So the high constellation zones of the rare earth element, including the Italy. So the final examples of that spectral and spatial downscale remote sensing image for detailed mineral mapping. So, but this topics is now presented yesterday for the IRGW as one of my topics. The challenge is how we can detect the key minerals, the ordination minerals that has correlated with the distributions of geothermal resources or metal resources. So for this case, we use the remote sensing technologies, because remote sensing technologies show us the reflectance spectra of specific minerals. So this is one examples of reflectance spectra. Therefore, this the green and the red show that the multispectral the data such as that Landsat or ASTA, very traditional remote sensing technologies. And this one is that hyperspectral, the reflectance. So obtained by advanced remote sensing technologies or drone, or airborne remote sensing. So of course, we want to use this continuous reflectance. Because using these continuous reflectance, we can know that the true features of minerals, and we can detect more details of where our target minerals exist. But the problem is like that here. The traditional remote sensing satellite image covered wide areas like that here. So it is very convenient, effective to regional extensive resource explorations, but not so good in the data. But hyperspectral data, as I said, excellent. But covered area is like that, very thin here. So our challenge is how we can combine too many wide and details. So for this case, we applied such a machine learning techniques. Two things. One is just such a traditional multiplier analysis, and now we're trying to improve this is deep neural network. My master course student tried to improve method, but this one is some multiplier analysis. So we determine the correlations or relationship between multispectral the informations and the hyperspectral informations, and using the Bayesian techniques that we could identify the best model. So the one example is like that. You may know that this cuprite area is a very famous area for test areas for remote sensing. Almost all body knows that the cuprite for the test areas. So when we propose new method, at first we try to apply these techniques to cuprite because there are many informations accumulated for this area. Now I visited there 2 times, here and here. So this is a result of the traditional remote sensing technologies, multiple data. Just showing potential probability of that existence of clay mineral and iron oxide mineral but cannot understand mineral names. Of course, the clay mineral composed of many the types such as monazite, kaolinite, things like that, but cannot know which minerals exist in this area. But this one is that the simulations from this data. But this is the simulation result from this data. So it's surprisingly that we can detect that very detailed locations of arenite. Arenite is that I'm standing on the arenite here. Arenite is here. And this one is that opal areas, hydrate silicate. And this is a kaolinite area and muscovite areas. But this is that the reference, the original the hypersphere data, and this one reference map prepared by geologists, by USGS. And these techniques extend to the porphyry copper deposit in Chile. As I said, this is the coverage by the multispectral image. And this one is the hyperspectral image. And there is a gap. The hyperspectral image is like that. So this is another problem. Our target is how that we can extend this hyperspectral image to wide areas, the covering porphyry copper deposit area. But this is a result of the simulations. That this is the original hyperspectral image. That this one is a simulated hyperspectra from the Landsat and ASTA data. So it is very interesting that there is no data, hyperspectral data, but that these data can simulate of hyperspectral informations that for the areas, no data. And but this is the examples. In the case of Landsat, it's maybe surprising that because originally this is just one boundary here, but using our the transformations based on machine learning, the Landsat can reproduce the spectra of arenite is like that, and this one is another type of kaolinite. And finally, is that mineral identifications and mapping. Using this case is ASTA data. But this is that ASTA-based mineral identified maps. This is arenite, opal, and the kaolinite like that. But this one is the Landsat-based the mineral identified maps. So finally, this techniques is that, this is on the way that we could not get final result. My PhD student tried to get more good result. So this one is try to select in the Australians. So this one is the covering areas is that ASTA image, multispectral image, and this one is that hyperspectral image. So challenge, as I said, how we can transform this hyperspectral image for that all areas of that multispectral image. So this one is that examples of that the original the multispectral image, and this is that downscaling, and also downscaling spatial resolutions and spectral resolutions. So difference is very little, but the please see that little bit clearly the image you can see this point and this point, and this one is that some band data, and this one is another band data. Little bit improved. For example, here and here, just a little bit. So we are now trying to this downscaling or spatial downscaling. The multiple downscaling is okay. So the original multispectral cannot detect mineral type, but for the spectral downscaling, these techniques could detect the distributions of kaolinite and muscovite like that. So I'm sorry that at first the 20 minutes we lost because of the problem of the network or my machines to connect So this is the summary that I introduced the variable structures, DNA, the deep learning neural networks for the clock deposit, and limestone interviews. And but interesting is that these techniques can be applied to detect inference factors and sensitive vectors. But these are effective for the generation process of that mechanism or generation mechanism of that such resources. The next one is that even though our data is very sparse, but neural query is hopeful. And that this neural query can be extended to whole Japan areas to 3D distributions of temperatures. So hopefully my PhD student from Indonesia, I asked him to please extend these techniques to whole Indonesia to clarify the 3D distributions of temperature. But unfortunately, the number of data is very limited to apply these techniques for all the Java or Sumatra the areas. So finally, that such a downscaling, spectral and spatial downscaling is the very good applications of machine learning to get more detailed information, so minerals related to mineral adjacent resources. Thank you very much for the kind attention and apologize again for the troubles for the past 20 minutes. Terima kasih.
Terima kasih, Koike Sensei. Thank you very much for your informative presentation. And I think your talk cover a lot of machine learning types, 4 of them, DNN, ordinary kriging versus self-labeling algorithm for network security, I think, SLNs. The third is clustering and spatial modeling, and the fourth is the downscaling of remote sensing image.
Yeah, right.
Yeah, I think there are many of interesting topics here packed in one lecture, but maybe one of you in this room or from the Zoom meeting could start. The first question to Professor Koike, please.
Please.
Okay, yes. Please state your name and institution.
Hopefully. Okay.
Talking to understand the definition of the type of or I know that the people that has information for mining in the area. What do you think? And in your presentation, you also mentioned about the use of machine learning when we are incorporating the direction filter to incorporate the controlling of the interpretation process.
Yeah.
What do you think about the use of machine learning if we don't have big data or we stay the PhD of the data? What can the application of machine learning to direct which in which area from this data we can have more data for next exploration process. So from the data we can use machine learning, and how do you think you can use for suggestions for exploration?
Okay, thank you very much. And similar questions I have been asking today and many researchers. So, the first thing is the applications of statistics and machine learning.
Sorry, Sensei, could you also, where the Okay, please continue. Yes.
Thank you very much for your questions. And as I said, the same questions I have been asked by the colleagues or students and the researchers. And this is a traditional applications of machine learning and geostatistics. So from the viewpoint of geostatistics, the geostatistics, they have the two merit. One is the produce, the estimation. And the other one is produce uncertainty. So uncertainty means that where is that high degree of uncertainty. So where is that low grade of uncertainty. So for this case, but this is also similar to or common to the machine learning techniques. The thing we use the several data, and of course, as I said, but biased data. And at first, we estimate spatial distributions. So of course, the important thing is that our target is the result of distributions or category distributions. In addition to the value or category distributions, another category is uncertainty. So for example, even though we estimated this point, the value is 10, but how is that the reliability of this 10? For example, from 9 to 11, or from 3 to, for example, 80, or 0 to 20 is like that. So to determine that the next target for that additional drilling or additional investigations is that the one measure is that such assessment of uncertainty. So the point, the point or zones that showing high uncertainty is the next target of additional information. So, and next point is that, of course, it depends on that our target. If we focus on anomaly zones such as Kuroko deposit or high temperature zones, the thing that we estimate, after estimations that we could find out the locations of high anomaly zones or high temperature zones. Of course, the next target is that the areas that showing such a high anomaly zones. But as I said, if the initial data is a number of the initial data is very small quantities and the biased distributions. So our the estimated anomaly is not so reliable. For this case, what we should do, what is that measure? So I think that as the applications of the Kuroko areas or geothermal applications, that we need to use the multiple information, so related to our target. For example, the target is Kuroko deposit, metal deposit. Of course, traditionally, we need to collect geophysical data, such as resistive data. Or, of course, such a deposit is related to geological structures, such as graben structures or uplift of magma intrusions. For these regional geological structures that can be interpreted, estimated by the gravity data like that. And also the surface manifestations can be detected or traced by remote sensing data. For this case, I recommend that many informations that related to your target. So not only geological survey data, not only borehole data, such multiple combinations that must be important, must be essential. Okay. This is my idea. Terima kasih.
Nurios?
Okay. I think your
Can I ask?
Oh yeah, Professor Hananto, please.
Okay, yeah. Professor Koike? Okay.
Yes.
It's very interesting topic, and I'm learning a lot from your
terima kasih.
presentation.
Terima
It's
kasih.
a lot of data you present here. Yeah. It's actually apply the artificial intelligence to targeting area, especially maybe our geology for the resource actually, yeah. But you also apply it for the geothermal as well as volcanic massive sulfide and seafloor. Yeah. I saw that you mentioned it's all depend on the data we input in the system, yeah, in the yeah, for the processing or the etc. Is it how? And I saw that the space of the data is very important because I saw that in your presentation there are many of real whole data, and then you analyze by artificial intelligence to targeting area. Is it something like that? Just a few to what your very interesting presentation. Thank you.
Thank you. Thank you very much for your comment.
Yeah.
Yeah. We try to advance our research to the many fields related to geothermal and metal resources and other energy resources. Okay, thank you very much for your favorite comment.
Okay.
Thank you.
Okay. Thanks for yours. That's all.
Terima kasih.
Just opening discussion for other maybe. Thank you.
Thank you. Thank you. Terima kasih.
Yes, yeah. Thank you, Professor Hananto. Yeah, I think we still have time to open one or two questions from this room. Maybe from Geoinformatics Research Center. While waiting. Oh, okay. Do you have anything to discuss? To be discussed? Okay. Professor Koike, a small question for me. I think years back when I was in Kyoto, Hyperion and pseudo Hyperion was really hype. Now, how is the advancement or maybe the development of the Hyperion or the usage? Are the images are free to be downloaded?
Yeah, Hyperion is, as you know, very old because hyperscalar data is about 22 or 23 years ago. So now we can use the latest hyperscalar data such as Hisui Japanese satellite and Prism, or German or Italian, or the United States, or some data are free, we can use, but some data are not free. But the problem is that the new satellite, the coverage area is still limited.
Okay.
So that the Hyperion is old, but the merit is that the many areas covered by Hyperion. That's why we still need to use Hyperion. So now I just read some of the papers with Alison and geosonics, and we could predict the earlier comment. Hyperion is old. Why use more advanced hyperscalar image? But we reply. Of course, we try to find out the more recent hyperscalar image. But our target is in Indonesia, covered by cloud, because this is the optical sensor image. So our essential problem is that how we can get cloud-free image. But it is very difficult for Indonesia or areas. Cloudy. And humidity, mostly we cannot see clearly the surface conditions. That's why that satellite image for the longer operation time period is better for our research. So in particular, the areas is Indonesia, where that tropical zones.
Yeah, that's right. Okay, thank you, Sensei. Or maybe our colleagues from Geoinformatics Research Center. Bapak, mau nggak? Ada komen atau discussion?
Mbak Rias nanya lagi boleh?
Oh iya, Pak Hananto, silakan.
Oke.
Maaf Pak, satu pertanyaan online ya. Silakan Pak.
Okay, yeah. I continue the question. Yeah, it's really not the question. Just something like a need. Yeah, because Japan, Indonesia is the same in the Ring of Fire of Pacific, yeah, and South Asia. So on your expertise, we hope you can help us to map the Ring of Fire of Indonesia. So I think we welcome. Thank you.
Okay. Yeah, of course, Indonesia is one of the best partners. And we have many Indonesian students from ITB and Surabaya. And now we are researching with such excellent students. Of course, we can advance the researches in the many fields or many topics.
It's not a problem, something from your government to our government, and then we can join research doing. That's the only idea. I don't know. Because we impose to the government. Yeah. Okay. Thanks.
Yeah, I agree, Professor Hananto. Yes, I think it's our dream. Later or sooner, we will be there. Thank you for your comments. Oke, mangga Bapak punten tadi, silakan.
Jadi, I just want to raise one questions regarding the development of models. Because I see in the presentation use models. Then our question is there any specific characteristic for each medium of the environment? So we have to detail the model. But in several environment, there is no model that can apply general problems of the information. So we have to detail the model depend on the data or the depend on the location environment. So we have the same problems.
Yeah. Thank you very much. Yeah, of course, you are right. Because there's no fixed or there's no universal model. But of course, that is the case of the method we use. So all method is not universal, versatile. So for this case, we use machine learning is better. And for this case, statistical or other method is better. So for the case of machine learning, as we said, that we try to change the model depending on the data. For the case of the critical reporting, I did two topics, three topics. And one is the DNS and SQL hydrogen deposit and the limestone mining. So the data is what the model, the different each with each area. For the case of the hydrogen SQL deposit. So for the case of then we could find the geophysical data, but such as resistivity. It's a very important. Because as you know, there is sulfide minerals. Sulfide minerals has a low resistivity. So by the definition,
metadata and the distributed data, but that's why that we incorporate this distributed data in our model. But of course, our target is limestone, such as not metallic resources. Of course, but other factors, such as, like I said, type of limestone. But this is the siliceous limestone, or this is such a marble marble that are limestones with influence factors is like that. And also we change our model that depending on the locations of the same. That because
Nanti bisa play dari YouTube nggak? Scan screen, share screen. Soalnya laptop gue masih dipakai santai. Ini gue email ke lo ya. Yang bisa dibuka apa?
The positive is that this area, the fractures, is the most important for the mineral distributions. And the positive is such as the distributions of hot springs and distributions of geysers like that is the most important. That's why we try to
mau dari YouTube bisa ke sini nggak? Dari Mas biar suaranya kedengaran juga apa gimana?
By changing the network structures, by using the data that we produce for the network, like that. So that's why even though the one study areas that we cannot fix just our model. So we need the change the model to get the reliable result. That's why that you are right. So that we facing the same problem that we can't fix just one model. Thank you. Thank you.
Terima kasih Bapak atas komentar dan pertanyaannya. Thank you. And then maybe we still have time to watch a video from
okay. Thank you very much.
Your laboratory, Sensei. Yes.
Okay, thank you.
We are going to watch this together.
Okay.
But maybe sorry, while we are preparing, I'm going to ask one question. So I think I'm dealing with geothermal recharge, Sensei, as you know. And do you think that number one method, DNN, can be applied to model the recharge mechanism? Because from water and then water interaction. I don't know.
I think that applying machine learning method is the second step. Most important is the geochemical method, I believe.
Okay.
So that machine learning method is not so powerful without good data. So at first, apply geochemical method, for example, as your specialist, such as isotope or trace element, strontium. So after that, of course, you can get the data, applications of machine learning to detect or such recharge areas, recharge elevations is maybe available.
Okay. Thank you, Sensei. So, is it ready?
Apply geochemical method, for example, as your specialist, such as isotope or trace element, strontium. So after that, of course.
Okay, we still have one last question from Dr. Purnama, please.
Yeah.
We just use software to
Okay. Okay, thank you. Well, thank you very much. My PhD student is now trying to do such a numerical program that can be easily used by other researchers. So hopefully that we can to complete this. At the present, this program is just closed by our laboratories, but hopefully we can improve this program that can be easily used for the other researchers. And I hope that this program that will be changed to public use. So please be forward. Or something like that. Yeah, like that. Yeah, not so complicated. No, not so complicated.
Maybe Dr. Purnama should try first. Okay, thank you for your response and your questions. And then how about it? How about it, Mr. Haris? Is it ready yet?
Thank you very much.
Hello, welcome to our laboratory environmental geosphere engineering. My name is Koike, professor of
Maybe Dr.
Graduate
Purnama
School
should
of
try first.
Engineering. Our society needs much natural resources.
Okay,
For
thank you
example,
for your response and your
metals for
questions. And
industry,
then how about
oil,
it? How about it,
gas, and
Mr.
coal
Haris? Is
for
it ready yet?
electricity generation and fuels, and water for agriculture and daily life. The demand of natural resources will be certainly increased more and more. Welcome to our laboratory environmental geosphere industry, agriculture, and economy. Professor of
Maybe Dr.
Graduate
Purnama
School
should
of
try first.
Energy, water resources. Our society needs and much natural resources.
Okay,
For
thank
example,
you for your response and your
metals for
questions. And
industry,
then how about
oil,
it?
we cannot
How
see
about it,
underground,
Mr. Haris?
so
Is
for
it
the
ready yet?
hydroelectricity natural resources is difficult, and water for agriculture technology to visualize the world. The demand of natural resources will be certainly increased. Welcome to our laboratory environmental geosphere industry extends around the area to see
Maybe Dr. Purnama should try first.
energy under control situation. Our society much more natural resources.
Okay,
But for example,
thank you for your
discover
response and
natural
your
resources
questions.
industry
And then
becomes
how
more
about
oil.
it?
We can
How
see
about
underground.
Mr.
The
Haris?
mission
Is it
of
ready
our
yet?
laboratory natural resources is different. The location for agriculture technology to visualize the world. The demand of natural resources. See underground. The mission of our laboratory natural resources is different. The location for agriculture technology to visualize the world. The demand. Applications needs interdisciplinary research is the covering science and engineering resources, but discovering new resources that becomes more and more difficult. Hello, welcome to our laboratory environmental geosphere engineering. My name is Koike, professor of Graduate School of Engineering.
It's good. So we can hear.
Our society needs much natural resources. For example, metals for industry, oil, gas, and coal for electricity generation and fuels, and water for agriculture and daily life. The demand of natural resources This will be certainly increased more and more due to global growth of population, industry, agriculture, and economy. Such metal, energy, water resources are stored in pores and fractures in deeply buried rocks from the ground surface. We cannot see underground, so the finding the natural resources is difficult and need advanced technology to visualize the world under our foot. Moreover, target of finding new resources becomes deeper and deeper and extends from land area to seafloor. Under a control situation, we need much more natural resources, but discovering new resources that becomes more and more difficult. The mission of our laboratory is to clarify the location, magnitude, property, and generation mechanism of the resources. This classification needs interdisciplinary researches covering science and engineering. Our researchers use latest knowledge and technologies of geology, geochemistry, geophysics, and mathematical modeling, and are based on field survey, laboratory experiment, data analysis, and computer simulation. Our target is both land area and deep sea floor. We have researches with many foreign students and researchers from Asian, African, and South and North American countries. Our laboratory member will briefly introduce their ongoing research. Let's start.
Hello, my name is Taikubo. I'm Assistant Professor of Koike Laboratory. My research topics focuses on the spatial distribution estimation and 3D modeling of geological information using a geoinformatics approach. In addition, we are actively incorporating advanced measurement equipment such as 3D scanners and multispectral cameras to explore new frontiers in resource exploration.
My name is Teddy Atma Pradana. I'm from Indonesia. Today, I would like to introduce my research about the spatial priority assessment of geothermal in Indonesia. And in this research, I'm using multi-sensor satellite imagery data, and also another parameter like land surface temperature, fault line, and also mineral exploration. So my goal is I will find new potential area in Indonesia, especially in Java Island.
My name is Masahide Kishimoto, a PhD student. This is one of the spectrophotometers, and we can get the reflectance spectra of visible and near-infrared spectra. We are using this device to detect the characteristic of substances.
Hello, my name is Vitor. I'm from Brazil. I'm a postdoctoral researcher at this lab. So my main projects focus on a mineral resource in seafloor. To achieve this or purpose here, you model the mineral resource applying geostatistical methods and the machine learning, deep learning techniques to optimize our available data. So I hope you join us for this outstanding project and make the difference for humankind society.
My name is Sylvie. I'm from Madagascar, PhD student. My research focuses on geometallurgy, and I use X-ray diffraction analysis to comprehend geological insight.
Hello, I'm Enatsu. My research topic is economic geology. And this is a scanning electron microscope. Elemental analysis also available in our lab. It can identify what kind of minerals are distributed.
Hi there, I'm Brenda, a PhD student from Indonesia. I'm currently doing a research on geothermal reservoir temperature estimations by fluid inclusion to identify the microtemperature, pressure, and composition of the rocks when it was formed thousands of years ago.
Hello, my name is Heru Beran Pratama, a doctoral student from Indonesia. My research focus on numerical simulation-based optimization of integrated framework for sustainable utilization of high-temperature geothermal system.
I'm Koki Kashiwaya. I'm the associate professor of this laboratory. My research fields are hydrogeology, geochemistry, and engineering geology. I have interests in environmental tracers and simulation techniques and machine learning to understand the subsurface fluid flow and mass and heat transport. And we apply them for sustainable and effective utilization of ground source heat and geothermal energy.
I'm Shun Yamamoto. I'm mainly researching about groundwater model simulation. I'm making hydrogeological model of Kyoto Basin.
Hi, I'm Yoshiaki Kawashima. Groundwater flow and heat transport analysis considering land use and land cover transition as well as the climate change has revealed the increase in subsurface temperature.
Thank you very much. My name is Nyora Donadi from Tanzania. To determine the origin of geothermal fluids, I use a cavity ring down spectrometer, Piccolo, to determine the values of deuterium and oxygen. Thank you.
Hello, I'm Muhammad Iqbal, PhD student from Indonesia. I'm researching the exploration of hidden geothermal system by using groundwater geochemistry. Here is water samples taken from the field. We use this machine ion chromatography to identify the major ion compositions, to interpret the reservoir characteristics of the geothermal system and groundwater system.
Hi, I'm Angga, PhD student from Indonesia. My research is focusing on supercritical geothermal system, and I'm using this equipment, permeameter, to measure the permeability of the rock samples. This equipment works by measuring the decline pressure from the injected gas into the rock samples.
We hope you are coming and researching together for sustainable future world with natural resources.
We hope you are coming and researching together
for a sustainable world with mineral resources.
Hey, what's a heartwarming video, Sensei?
Hopefully you enjoy this video.
Yes, okay, thank you.
Yes. That the Kashiya Sensei is now trying to apply machine learning.
Machine learning,
So there
yes.
is some additional comment or a perspective
Sure.
to apply machine learning
Okay.
for his research. Geochemistry.
Okay, okay, Sensei.
There is microphone.
I think yes.
Thank you very much. I'm associate professor at and I'm just so yes. And it's very fun and I'm happy to see the yes very excellent and as I explained in the video, I have understanding of the source and calculation of the sample and now I'm applying kind of machine learning unsupervised machine learning because we cannot understand what processes affect the excitation of something. So I selected unsupervised machine learning. So its name is and now I am applying the ICA to understand what processes are included in hydrogen chemistry and to demonstrate to estimate the original condition of analyzing states. And then I will share the recent result presentation and after we start some things I will thank you very much. I hope we can start some on the
Thank you, Dr. Kasiwaya. Maybe participants from the Zoom could not hear you, but but I could convey your message that the geochemistry analysis now can be merged into the machine learning, and then we can join to start this project with Dr. Kasiwaya in Kyoto University. I think that's all for today. As we come to the end of the this lecture, I'd like to thank once again to Professor Koike, Dr. Kasiwaya, and our esteemed guests. And I think we believe this stimulating discussion benefited geoscientists and data scientists, as well as industry professionals and students. So let us consider this the start of future partnership. Thank you for joining us today. I'm sending off for your screen. Bye.
Okay, thank you. Ibu Dr. Diostantika. And we would like to thank you to Professor Koike for bringing us to a very productive session today. So ladies and gentlemen, we are currently in the closing session. We would like to remind you that the link to attendance report form is available and active. The link has been appended in the chat column. On behalf of the committee in charge, we would like to express our apologies we made during the event. Thank you very much for your active participation today and have a great day. See you in the next program. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Terima kasih BRIN, Pak.